So we start off today with regularization, which, as we know, helps us control that bias variance trade-off. And we talked about two categories of regularization, one in which the penalty term is the L2 norm of the coefficients, and one in which the penalty term is the L1 norm of the coefficients. And then we actually looked at, we actually briefly mentioned, but didn't really discuss, another regularizer which combines both of the two. So today we're going to look more at what adding a penalty term does to a cost function and how it reduces variance. So to start off with, we'll look at the ridge regression, which has an L2 penalty term. And we'll focus mainly on how it helps when you have features that are fully or partly collinear. We thought collinear features a couple of times before. We saw them in our case study on linear regression with the teaching evaluation data set. In that data set, we saw that there were attractiveness rankings for each individual instructor that were extremely collinear. And we saw that as a result, the coefficient value kind of canceled each other out. So we had, let's say, many large but opposite coefficient values for each of the individual collinear features. And then we also saw an example when we looked at gradient descent about how collinear features makes it difficult to find kind of a single set of optimal features, because when you have collinear features, you can have, let's say, multiple different coefficient values that still produce the same result. So that means that depending on, a little bit of noise in your training data, one time your estimate might come up with one set of coefficients, another time your estimate might come up with a totally different set of coefficients. So we'll look at this by example using L2 regularization. Now I'm generating some data with 5 features, and the first 3 features are independent. The last 2 features are going to be extremely collinear with a randomly selected column from the first 3. So this is what this data set looks like. So here we can see pretty clearly, if you look at, let's say, these bivariate plots of each variable against each other variable, we can pretty clearly see this collinearity between, let's say, x2 and x4. And here's another example of a, let's see, collinear one as well. So we have 2 collinear features here. And in this example, we can actually kind of see the collinearity looking at the matrix of bivariate correlation coefficients. So you can compute the correlation coefficients for each variable against each other variable. Now, obviously, in the diagonal, you have all ones because every variable is perfectly correlated with itself. But in the other entries, you can see, for example, a high value for x3 and x4, which are highly correlated. Sorry, x2 and x4. And also for the last and the first variable. Now, I'm just going to mention briefly that this only works well to look at the correlation coefficient when you have a single feature that's correlated with one other feature. Sometimes you have a feature that's a linear combination of multiple features. That's called multicollinearity. And it's difficult to identify just from a pure plot or from a correlation coefficient. So for multicollinearity, there's a metric called the variance inflation feature, where a large number indicates multicollinearity. Okay, so here you can see, for example, that 2 of our features have multicollinearity. Okay, so we know from our previous example that when you have collinear features, we can look at these MSE contours over the feature space. So this is a quick simulation. Okay. So suppose we would do a linear regression and pick a random pair of coefficients from this feature space. This is what our mean squared error would look like. The case on the left is two collinear features. The case on the right is two independent features. And we can see, as we've seen before, that when you have collinear features, you end up with a very strange loss surface where there's a very large range of coefficients with a similar mean squared error. The star in both cases marks the true coefficient values, by the way. So when you have very collinear coefficients, very collinear features, I'm sorry, then you have many possible pairs of coefficients that all have similar mean squared errors, which means that your estimate of the coefficient values can end up anywhere in this very large range, and that leads to high variance. To emphasize this, we're going to look at a simulation here. So this is a simulation that will compare a model with one feature and a model with two collinear features. Let's do a quick poll. So here we're looking at model A with one feature, model B with two collinear features. Now, both of these examples, the model and the data match. So for model A, we have data with one feature and we're training a model with, let's say, W0 plus W1 X1. Model B has two collinear features and we're training a model with W0 plus W1 X1 plus W2 X2. Take another few moments to vote. Okay. I'm a little surprised at the results here because no one got the correct answer for the first part. Our expectation is that over infinitely many training data sets, both of these models should be unbiased. We know that for a linear regression, as long as there's no under modeling, the model is unbiased. So let's see if that's what we observe in fact. Okay, so yes, that's right. So we see the true function is a black line. The mean of many models is a red line. And they're basically identical. So both of these models are unbiased. Now, we're not averaging over infinitely many training sets, so it's not like literally zero, but it's very close to zero. And as we would average over more training sets, we will get closer to zero. But the majority did correctly understand that the model with two collinear features has more variance than the model with only one feature. Now, I want to emphasize here that the second feature in model B doesn't really add any new information. It's just the scaled version of the first feature, right? But even though it doesn't add any new information, it increases the variance of the model. So let's see how this all changes when we add our L2 penalty. So we had these mean squared error contour plots from before. This is a case with, let's say, collinear features. This is a case with independent features. And now we're going to compute the L2 penalty term on top of our mean squared error contours. And we're going to plot it. Okay. So now we're overlaying this penalty, these black and white contours on top of the mean squared error contours. And notice what this does here. So for this case with two independent features, the white star marks the optimal point for the mean squared error. And the center of this white circle marks the optimal point according to the penalty term. So let's draw that. Okay, so I'm going to draw a plus here. This is the optimal point according to the penalty term. For the case with two independent features, well, you could see that you would typically have kind of found a value somewhere in this region anyways, because of the MSE contour shape. But the regularization term will kind of, depending on the strength of the regularization factor, that alpha, might pull the estimate towards this point. But what about over here? So over here, notice that originally you could have found a optimal pair of coefficients kind of anywhere in this range, even though the true optimal is where that star is. Because of noise in the training data, sometimes you can be, displaced from that star. And because the mean squared error anywhere in this range is so similar, you could have found a coefficient value anywhere. But now with the L2 penalty term added on top of that, so these regions here are kind of no longer desirable. Your optimization is no longer going to find a point in those regions because the L2 penalty is much larger there. So now your optimization is really only going to look in this much smaller region, which means we're likely to have less variance, right? Because instead of estimating a pair of coefficients in a large range, we're now going to look at a much smaller range. Let's do a simulation again to see how that works. So here's, by the way, the sum cost function with the mean squared error term and the penalty term. So we're going to do a simulation here. I'm going to ask you in a moment to answer in a poll which one will have more bias and which one will have more variance. The least squares linear regression on two collinear features, or the least squares linear regression on two collinear features, but with an L2 penalty term. Take a few more seconds to vote. So let's take a look here. Now, a moment ago, I told you that for a least squares linear regression, as long as there's no undermodeling, there's no bias. But once you have a regularization penalty, notice now the true optimal, let's say the true optimal coefficients are no longer at the very minimum of the cost function. The cost function has the effect of dragging the estimate away from the true values and towards the origin of the coefficient features of the coefficient space. So that actually introduces bias. There's some systematic error in the model in which it's systematically underestimating the coefficient values. And we'll see that here. So here you see a kind of, actually here you can't see it at all. Let's actually change this a little so we see it a little better. See, what was W true here? I'm going to pick some larger coefficient values so you see it a little bit. Let's try that again. While we run that again, let's take a look at how we actually compute this here. So you'll notice a common pattern for all of our sklearn models. Okay. So previously we used linear regression. For a linear regression, you create a linear regression instance. Then you call fit and you pass the feature set for the training data and then the vector of labels for the training data. And then you could call predict on the test data. Now, every scikit-learn machine learning model works the same way. Sometimes you might have some extra hyperparameters you can pass. Like for example, for a regularized model, you can pass the value of alpha. But they'll all work the same way in that you declare an instance of the model, then you call fit, and you pass the training data, the X and the Y of the training data, and then you can call predict. So that makes them very easy to use because now that you know how to use one sklearn model, you actually know how to use all of them. So this works for linear regression, it works for ridge, it works for lasso, it will work for the logistic classifier we're going to use in a moment. It will work for all of them. Okay, let's take a moment and look at our simulation results. Okay, so here we can see the bias much more clearly because the coefficient values are larger. Model A is a regular least squares estimate of the coefficients. So the true function and the mean of the models are basically identical. Now, again, we're not training over an infinite number of training sets, but as the number of iterations of the simulation will go to infinity, the true function and the mean of the models would be identical. So the bias of the least squares estimate is essentially 0. The variance, on the other hand, is very high, and it's especially high because of the collinearity of the features. Now, what if we look at the model B here, which is the least squares, but with a L2 regularization penalty term. So notice here that this model is biased. Right? The coefficient terms are kind of pulled towards 0, which introduces a systematic error in the model. So if you run this estimator many times on new independent training sets from the same distribution, the mean of all those estimates is not going to be the true function. Here is a true function. The mean of the estimates is here. You could see that the mean of the estimates is at the coefficients tend towards smaller values than their true values. On the other hand, the variance of this model is much less. Right? For model A, which is two collinear features with no regularization penalty, the optimization procedure might find kind of any of a wide range of pairs of features. For model B, which has a regularization penalty, the optimization is going to look in a much smaller region. And as a result, we can see much less variance. You could see these orange lines, which represent the individual models, are not as widely distributed around the mean. And also looking here, you can see the variance is much less. So the overall error of model A is actually much greater, even though it doesn't have this systematic error. Let's see, Elena there's a question in the chat. This is actually not a logistic regression. This is a regularized regression. And yes, so it's absolutely true that even though there's a systematic error, it could still have smaller mean squared error if the variance is smaller. So remember that the total error is composed of the squared bias, the variance, and the irreducible error. And here, by adding the regularization term, we increase the bias term, but we decrease the variance term. So depending on the relative magnitude of those increases or decreases, it might be worthwhile to add bias. Okay, there's another question. For model A, is it true that some of the L2 are less than 0? I'm not sure what that question is. In model A here, there is no L2 penalty term. So it's just a regular least squares linear regression. Does that answer the question? Okay. So we can see here that the L2 penalty term adds bias because it pulls the coefficient estimates towards 0 and away from the, let's say, optimal value according to mean squared error alone. But it also reduces variance. And depending on whether your model has high bias or has high variance or not, that might be a worthwhile trade-off. So this is kind of a very difficult thing for people to wrap their heads around. Why on earth would you want a model with systematic error? But you can see that in some cases it really helps. Now, I mentioned in the lecture that we have to standardize inputs before using a regularized regression. And that's because we know the L2 penalty term disproportionately shrinks large coefficients, right? So the L2 penalty term looks at the square of the coefficient values. And so it pulls more strongly on large coefficients than on small coefficients, right? If you have one coefficient value that's, let's say, 5 and another coefficient value that's 0.5, the 5 coefficient contributes much more to the L2 penalty term because of that square. And so you get much more benefit from decreasing the 5 coefficient than the 0.5 coefficient. So this is problematic because if you have features on different scales or in different units, then you could have coefficients on wildly different scales, and then you might end up with, let's say, totally different results depending on the units of your data. So to prevent this, we usually standardize inputs by subtracting the mean and then dividing by the standard deviation. Now, here's an example. So in this example, I'm going to apply a ridge regression to some data set where the, let's say, one coefficient is much larger than the other coefficient. So you could see that the coefficient values, the true coefficient values are like 0.2 and 2. Yeah, they're 0.2 and 2. And you could see that the ridge regression as alpha increases pulls much more strongly on the large coefficient value than on the small coefficient value. So now we're going to standardize the two features, the x1 and x2 features, so that it doesn't happen. Fortunately, since we know how to do a linear regression, we already kind of know how to use it. So the scalar, the standard scalar that comes with sklearn is kind of similar to any of the machine learning models. So it still has a fit method. So we can declare a scalar, then we can fit it. And then we're not going to, let's say, predict anything, but we are going to transform things. So we can fit our scalar on our X data and then transform the data. And now we have standardized data that's mean removed with unit variance. And that means that the coefficients are going to be kind of similar. And the ridge regularizer will kind of pull on them both equally. So this is a demonstration of why we standardize inputs. Okay, are there any questions on the L2 example before we move to the L1 example? So we said that the L2 regularization is really helpful when you have kind of a annoying cost, like loss function surface. For example, here we have a loss function surface that has a long, deep valley in it. Now, this is for mean squared error. You could imagine if we were looking at the, let's say, R squared value instead of the mean squared error value, it would look like a long, narrow mountain, like a ridge. That's where this kind of regularization gets its name. The L1 penalty regularization is helpful in a different way. We said that the L1 regularization helps by zeroing out some coefficients. So it's very helpful when you have many features where some of them are uninformative or unimportant. Let's remind ourselves of this. So we're going to do another simulation with two examples. In model A, you have a least squares linear regression, so no regularization term. It's trained on one feature, and it's an informative feature. Okay. So the true function is, let's say, y equals w0 plus w1 x1. And we're going to train a model that's y equals w0 plus w1 x1. Okay. I'm going to actually write that in here. So we have 2x equals so we have a least squares linear regression trained on one informative feature in the first case. In the second case, we have a least squares linear regression trained on one informative feature and 5 uninformative features. What does that mean? It means we're going to have a W2 x2 plus W3 x3 plus W4 x4 plus W5 x5 plus W6. Okay. So in both cases, the true function is, one informative feature. But in the second case, we're training our model with the addition of some uninformative features. Now, is this model capable of capturing this true function? Is the true function inside the assumed model class? So think about that when deciding which one has more bias and more variance. And let's see how we vote. Okay, take a few more seconds to vote. So in this case, I would agree that there's no under modeling here and there's no penalty term here. So I would agree with 40% of you who said that both of these models will have the same bias. I would expect both to be unbiased. But model B will definitely have more variance because it had more parameters. And we said that for a least squares linear regression, the variance increases with a number of parameters. So let's see how that looks. Okay. So in both cases, there's essentially zero bias. Okay, remember, we're not truly averaging over an infinite number of training data sets, which is why this number is not exactly zero. But as we would increase the number of iterations of our simulation, this number goes to zero. And that's because the true function is basically identical to the mean of the models. But if you look at the variance, in the second case where you train your model on more uninformative features, you could see that the individual models vary more around the mean. So the individual orange lines vary around the red line, much more for model B than for model A. And that's reflected in the mean squared error as well. And that's because even though the true coefficients for, let's say, W2 plus should be zero, because of the noise in the training data, you might estimate a non-zero coefficient, and then you end up with variance in your model. So let's see how the L1 penalty helps with that. So we're going to try the same two models here. But now we're going to add an L1 penalty term to our loss function for training the model. So I'm going to relaunch the poll. And you're going to tell me how you think the results, sorry, it's not going to be the same two models. It's going to be this model again. Okay. But model A is just the same thing. Model B is with an L1 penalty term. So in both cases, we have a model trained on one informative feature, 5 uninformative features. But in the second case, our loss function will include an L1 penalty term. Yes, exactly. Model A this time is what model B was last time. Okay, take a few more seconds to vote. Okay. The majority of you agree that the regularized regression has more bias. And I think that will be the case because the regularization penalty introduces a systematic error by pulling the estimate towards the origin. But the first model, which has no regularization term, will have more variance. Let's see how that looks. So here we can clearly see the bias in model B. So the black line is a true function. The red line is the mean of all the models. And we can see that bias pretty clearly. There's a systematic difference between the true function and the mean of all the individual models. On the other hand, the orange lines, which are the individual models, don't vary as much around the mean model. So we could see, in this case, actually, the mean squared error ends up being pretty similar, but model B, even though it has some systematic bias in it, has a slightly lower mean squared error because of lower variance. Now, we had lower variance with Ridge 2, but with Lasso, it's for a different reason. Let's see why it actually reduces the variance. So we're going to look at a couple of linear regressions with an L1 penalty term. Now, first, we're just going to look at the regular mean squared error contours. So I generated a couple of sets of linear data, and these are the mean squared error contours. So this is the true coefficient pure. And these contours show what the mean squared error would be for any other coefficient pure in this space. Now I'm going to overlay the L1 penalty term on top of these contours, just like we did before. So notice that just like the L2 penalty term, the L1 penalty is centered at the origin. So it pulls the coefficient estimate away from the true value towards the origin. However, notice that the shape is different. Since the shape is different, the path of the optimization becomes different as well. So I'm going to plot the path of the optimization as alpha increases. So for the L1 regularization, as alpha increases, for alpha equal to 0, the L1 penalty term is zeroed out, and we end up at the true coefficients. As alpha increases, we start to decrease both coefficient estimates equally. Right? With the L1 penalty, both coefficients contribute equally towards the penalty term. It doesn't matter if they're small or large. So we start off by decreasing both of them equally until the smaller one actually reaches 0. Once the smaller one reaches 0, it continues at 0 while we then continue to decrease the other one. So the L1 penalty term has the effect of increasing what's known as sparsity, meaning the number of non-zero coefficients, by zeroing out some of the coefficient values. We can see it a little more clearly if we plot that regularization path on top of the overall loss function, overall cost function. So this is an overall cost function, including both the mean squared error term and the penalty term for some value of alpha. Okay, so we can see that in this region, the path of greatest descent is kind of here. So as alpha increases and we're pulled more strongly towards the origin, we go here. Now, eventually we hit this part where it's like a crease in the cost surface. And once we hit that crease in the cost surface that's caused by these sharp edges, we stay in that crease. So once one term is zeroed out, it will stay there. Okay, are there any questions about the L1 regularization? We're going to look at a 3D visualization to help us kind of conceptualize this a little better. So I'm going to choose a pair of coefficients. Let's say I'm going to choose 5 and -3. And I'm going to generate a set of MSE contours and a set of, let's say, penalty term contours here. And then let's create a plot of these. Okay, so here's my plot. Now, for now, I'm just looking at the cost surface. I'm going to use smaller coefficient values so that we could see it more clearly. Let's use 2 minus. No. Now I'm also going to adjust the range here. Okay, let's adjust this range. Okay, so this is a mean squared, this is the cost surface. Now, currently I have alpha set to 0, which means that I'm essentially looking at an unregularized least squares linear regression. And let's just change the view a little bit. We could see that this cost surface has its minimum, right around here, which is where I set the true penalty terms. I'm going to change those to bigger values again, now that I adjusted the scale, just so that it's a little easier to see what's going on. Okay, so this is a little easier to see. So here I'm looking at the cost surface with no regularization because alpha is 0. And we could see the minimum is somewhere around here, which is where my true coefficient values are. Now, let's stop looking at the cost surface for a moment. So this is a mean squared error surface alone without the penalty term. Now, I'm also going to show the penalty surface. So this shows the contour plot of, let's say, the penalty term for the L1 penalty term. What is it going to look like as I increase alpha? Okay, so here, higher values on this cost axis means larger cost. As I increase alpha, so the mean squared error term in the cost function will stay constant, but the regularization term will change. For this L1 penalty, let's look at just the regularization. And let's look at an overhead view here. Okay. For the L1 penalty, as I increase the alpha of the regularization, the corners are kind of pulled up along these really like interesting sharp creases. So it essentially makes this kind of weird little square shape, or this weird little like pointy shape, right? Because of that L1 norm. So as I increase alpha, right, we start with just this mean squared error surface. And by increasing alpha with this L1 penalty term, I'm starting to add that penalty surface that's shown on the bottom. And those will be added together to produce this cost surface. So putting this all together, as alpha is 0, the penalty surface is essentially flat at 0. And the cost surface for the regularization regression is the same as the mean squared error surface. And now as we increase alpha, we're adding together those two terms to produce this kind of combined cost function. That's the mean squared error plus the regularization penalty surface. And we could see as we look at it from maybe a different view, that the optimal point has changed. So originally with alpha equals 0, from this overhead view, we can kind of see how the lowest point in the cost surface changes. With no regularization, the optimal point is over here, right? I set it to, let's say, -5.2, I believe. Let's check. Oh, sorry, 3 minus 4. Okay, so the optimal point is here at 3 minus 4. That's where it's, let's say, most purple. As I increase alpha, the optimal point is going to be dragged towards the origin. So you can see the purplish part moves towards the origin as the L1 penalty pulls up the corners of the cost function. So you can play around with this later to try and get a feeling for how that penalty term works. Let's look at the same thing with the L2 penalty term. So here's the L2 penalty term. Once again, I have my mean squared error surface and my regularization penalty surface. And as I increase alpha, so the regularization penalty surface, again, increases by pulling up the edges, but with a very different shape because the L2 norm has a totally different shape. So here, as I pull up the edges, I'm kind of creating this like nice little oval surface, which has a very different effect on the overall cost surface. So this will end up looking something like this as I increase alpha. Okay. So are there any questions on the regularization section of today's lesson?